All right, practice exercise 102 as we get started today. Exercise 102 there at the bottom of page 28 in your practice exercise booklets. Quick refresher there at the top of the exercise that the three angles of a triangle add up to 180 degrees. So you're going to use that knowledge to find the third angle of each triangle in that top row, several problems there. Then they've given you the three angles of some triangles. They want you to classify the triangle as being either an acute triangle, an obtuse triangle, or a right triangle. And then finally at the bottom, two word problems. They're going to kind of blend algebra and geometry together. Going to get started, exercise 102. right, go and put your pencils down if you would, please. In fact, if you'll set those aside and get out a pen. Pencils away, go ahead and take out a pen. I'm going to make this a practice quiz, meaning you can count this one if you want to, but you don't have to. In fact, I'm going to let you count it, some of you, in place of practice exercise 96, which we did a few weeks back. It was a pretty rough exercise, you might recall. So I'm going to let you count this instead of that. So pencils away, pens out. I'm going to let you grade your own. That way you can decide whether or not you want to count this. I'm going to go ahead and give you the answers, and then we'll see how we did. Top row, going across. Your answers should be 90 degrees, 80 degrees, 60 degrees, 90 degrees, 60 degrees, 78 degrees. And those are 8 points apiece. So off to the side, write the number of points off. There are 8 points each for the top row. So if you missed 0, write -0. If you missed 1, write -8, -2, write -16, that kind of thing. The next one going across, these are worth 5 points each. What type of triangle do we have? Well, the first one would be a right triangle. The next would be an obtuse triangle. The next would be an acute triangle. Now, it does happen to be equilateral, but it asks for acute, obtuse, or right, so acute is the answer. And the last one is right triangle. So right, obtuse, acute, right. They do happen to be a couple of isosceles in there, but that wasn't what was being asked. Again, those are 5 points each. So write the minus number off to the side. Again, hopefully -0. For number 15, asking how many degrees are in each angle of an isosceles triangle. Your answers are 36 degrees, 72 degrees, and 72 degrees. Let me show how that would be worked very quickly. We've got 2 base angles, and each of them contain twice as many degrees as the third angle, or the vertex angle. So we've got a vertex angle, we've got a base angle, and we've got another base angle. And each base angle contains twice as many degrees as the vertex angle, or the third angle. Call that x. If they each contain twice as many degrees, they would each be 2x. And we know that together, they all add up to 5x, 180 degrees. So x is 36, and that's how we get 36 degrees, 72 degrees, and 72 degrees. That's worth 15 points. 15 points. If you got it, good. If not, -15.
I just put 36 for like the x. I didn't put
Oh, you got as far as the 36, but you didn't list all of them? Let's call that -5.
Okay.
That's probably how I would grade that. All right, any other questions? All right, then on the last one, third angle of a triangle contains twice as many degrees as the first angle, and the second angle contains 20 degrees more than the first angle. By the way, first angle should be x. How many degrees in each angle? 40 degrees, 60 degrees, and 80 degrees. 40 degrees, 60 degrees, and 80 degrees, and that's worth 15 points if you got it. Again, we've got first angle, second angle, third angle. They all come back to the first angle, let that be x. Second angle contains, third angle contains twice as many degrees, and the second angle contains 20 more degrees. Altogether, 4x plus 20, they must add up to 180. Subtract the 20 to get 160, divide by 40 to 40, 60, 80 degrees. All right. How many of you say, I would like to count this in place of my previous practice exercise, or I'm actually good with my adjusted practice exercise grade, and I'd like to add this to the other grade. I'd like to use it as an extra. How many would like to count in place of?
That was 15 points, right?
The last one was 15 points, yes. How many would like to count in place of the previous exercise?
You made the same.
All right, so I've got a couple of you. Let me write this down on a sticky note real quick. So Quentin and Chris, throw out the old exercise, count this instead. Chris and Quentin, replace. All right, gentlemen, let me go and get your books from you, and I'll set those aside so I grade them. How many say, hey, I did great on this. I'd like to count it just as a standalone quiz. I'd just like to count it. All right, Jamie, you did a great job, and you like your old grade as well, so you want to count both. All right, and
Made the same grade, so
all right. So the rest of you are saying, I don't want this to count. We're good with it not counting, okay? Are there any questions on the exercise then? Those who did not do well, are there questions? All right. Chris, did you get 100? No, but still did well, just not 100, okay? Quentin, you were second. Did you get 100? You did. All right, so great job. Except for catching it. All right. We blame the hoodie. It's the hoodie's fault. All right. We'll give him an excuse because it's his birthday. All right, questions on this? Questions on this? All right, let me go ahead and collect those from you then. Take out your notebooks, if you would, and open up to Theorem 75. Open up your notebooks to Theorem 75 and those two corollaries that you copied last night. Copied out Theorem 75 and a couple of corollaries. Go over those just very quickly and then we will move on. And Chris, why don't you go ahead and read Theorem 75 for us?
The square on the hypotenuse of a right triangle is equal to the sum of the squares of the two legs.
Good, and the idea here is that the square on the hypotenuse is equal to the square on one leg plus the square on the other leg. But we know that the area of a square is found by side squared. Well, what do we call the hypotenuse? Call it C. So the area of the square would be C squared. What would be the area of one leg? Well, if we call the leg A, its area class would be A squared. What would be the area of the other leg? The other leg's square, B squared, right? And this is essentially, now we already have the Pythagorean theorem. So for us, we use the Pythagorean theorem to prove this. But this could be used instead to prove that the Pythagorean theorem is true if you went through all the rigmarole, and we won't take time to do that in this lesson. Most years I would, but we're kind of crunched for time. Look at Corollary 75.1. Read that for us if you would. Genesis.
The square on one leg of the right triangle is equal to the square on the hypotenuse diminished by the square on the other leg.
And very simply, you just move one of the legs to the other side so that the other one leg square equals the square of the hypotenuse diminished by, great word, the square of the other leg. So pretty straightforward. Then Corollary 75-2. This is kind of interesting, actually. Ethan, read that for us.
If similar polygons are constructed on the three sides of a right triangle, the sum of the polygons on the legs is equal to the polygonal hypotenuse.
Yeah, this one's kind of interesting there, that you could take any polygon on, it doesn't have to be a square, just any polygon area would be equal, on the hypotenuse would be equal to the areas added together of the other two. And the reason is that areas to area, side squared is to side squared, right? And so taking the side squareds would equal the areas and so forth, or be analogous to the areas. Interestingly, in your homework reading, did you catch that a U.S. president actually put together a proof of the Pythagorean theorem? Did you notice who that was?
Garfield.
President Garfield was apparently a bit of a mathematician tinkering around, and he actually came up with, if you're looking at page 249, go ahead and turn there, we're going to be there in just a moment, one of the many proofs of the Pythagorean theorem. There are over 70 different ways the Pythagorean theorem can be proved. Now, we proved it the traditional method that Euclid included with the elements, because it built very naturally upon Theorem 61 with the segment is to altitude as altitude is to segment, and segment is to leg is to hypotenuse kind of thing, right? But there are over 70-something different proofs, and President James Garfield came up with one of those. And you see there that little figure 2, he used that sketch of a right trapezoid to find that, to do that proof. So kind of an interesting way there. All right, let's go ahead and quickly review over our area formulas. We have a test coming up in just a couple more lessons, lesson 167, that's Wednesday. So let's quickly recap our formulas. And a rectangle, what's the area formula? Kendall? All right, what's the square, Audrey? S squared. What about parallelogram, Quentin? PL equals BH. What about the triangle, Chris?
T equals half of B plus H, or BH.
Good, T equals a half BH. Genesis, the trapezoid.
TR equals 1/2 H times B plus B prime.
Do you remember the other trapezoid formula, Jamie?
TR equals HM.
Good, we could just do altitude times median if we happen to have the median. We usually don't, but if we did, we could use it. What about the, is that our last figure?
Rhombus.
Oh, rhombus, there we go. What about the area of a rhombus? Thank you.
RH equals 1/2
Yeah, that was the last one that was a theorem. This was in an exercise. In fact, right triangle was also in an exercise. Back to Genesis.
TRT equals 1/2 leg 1/2.
There we go. And of course, if we were to compare figures to each other, you know, r is to r prime is b, h is to b prime, h prime, and so forth. Remember here, the halves would drop out. In general, for similar polygons, how would I compare the areas to each other, Kendall? Audrey? There we go. So these different formulas you want to make sure that you have memorized for that test coming up in a couple of lessons. Let's go and take a look at the homework now, though, that you had on page 249. You did numbers 4 and 5, a little bit more interesting problems here. And go ahead and read number 4 for us, if you would, Jamie.
The area of triangle ABC equals 36 square inches. If AC equals 8 inches and AD equals 3 inches, D being on AC, find the area of triangle ABD.
All right, so we've got this triangle, and we know side AC. That's the only side we know of the triangle. And we know there's a point on AC called AD. So I'm going to go ahead and draw AC down here. And we know, Jamie, that AC is how many inches? 8 inches. But there is a point D on this line such that AD is 3 inches. So here would be half, that'd be 4 and 4, right? So I'm going to come over this way, and we'll say it's 3 and 5. Make sense? Okay. And then the triangle goes up to some other random point B, which we really don't know anything about. And it just goes up there somewhere. In fact, it could be an obtuse triangle for all I know. I really don't know much about it. But I know that the whole triangle has what area, Jamie?
36 inches square.
And the question is, what would be the area of triangle
ABD.
ABD? That's what we're trying to find. Thoughts on how we could find the area of triangle ABD? There's a couple ways we could do
I
this.
already messed up, so I put C as my vertex angle. So I already.
Well, you could have rotated so AC was on the side. Like if I look at it this way, AC is on the side. That's fine. It doesn't have to be that way. I will say, strategy tip, it will help you if you know a side to make it your baseline, if you can rotate the figure that way. Now, a trapezoid's a little awkward to rotate, right? We did work with a rotated trapezoid. Remember that one with the triangular tract of land, and we drew perpendiculars down? And okay, we've done it, but it really does throw us off when we rotate a trapezoid. But all other figures really can be rotated fairly easily. Thoughts? Let's go to Ethan. You got 100 on your last quiz. You're smart, right, Ethan? Ethan, smart boy. Tell us. Go and tell us. What do you think?
Well, we have the area of ABC.
Mm-hmm.
So we could do 36 inches squared equals 1/2, 5, and then 8. Because 5 is basically.
Is 5 the base of triangle ABC?
Oh, I was thinking BDC. 8. Have 8 that I had wrong. 8 and then 8.
There we go. I don't know the altitude of triangle ABC, do I, class? But I know the base could be 8 if I rotated the triangle, so I could find the altitude. I could cancel the 2 and the 8 to get
4.
and I could find that if I rotate it this way, the altitude happens to be
12 inches.
divide both sides by 4. Divide away the 4. Divide away the 4. It's 36 divided by 4.
Sorry, my brain's slow.
Class,
9.
9 inches. All right, it's okay. It's a Monday.
I thought it was 12.
He used up all his brain cells on that last quiz. That's not a good time for the test tomorrow, or in 2 lessons, but yeah, 9 inches the altitude. So then, let's come to this triangle. What's its base, class? 3, obviously. What's its altitude? Well, here's the vertex, here's the base, and altitude is the perpendicular from the vertex to the base. What's the altitude?
9 inches.
9. So the area of the triangle equals a half base times altitude What's the area, class?
27. 27 is
27 halves, or
13 and a half.
and is that inches squared?
Yes.
Inches squared. Anyone have 13.5 inches squared?
I was so close.
Nobody. Okay, does it make sense now? There's another way to look at this. Those two triangles have the same altitude, don't they? And the areas of two triangles are to each other as the products of their bases and altitudes. But if two triangles have the same altitudes, they are to each other as their bases. Area is to area as base is to base. And I could have done it with a proportion. Either way works. Questions? Let's take a look at number 5. Read number 5 for us, if you would. Were there any other hundreds on that quiz? Nobody wants to raise their hand anyway. All right. Let's see.
The quiz Monday? Thursday?
The quiz I passed back at the beginning of it. You did. Okay, James, number 5. Actually, you just read number 4. You read number 5, and she'll work number 4. How about that? You read it.
ABC is an isosceles triangle. Base BD equals 16 inches, and altitude on AB equals 6 inches. If BC is extended through C to D so that CD equals 4 inches, find the area of the triangle CDD.
All right, so clearly this is kind of a convoluted picture here. We start, though, Jamie, by drawing,
an isosceles triangle.
and we call it,
ABC.
1, 2, 3.
and what do we know about our isosceles triangle?
AB is 16 inches.
AB is 16 inches. Good. Then what do we know?
The altitude is 6 inches.
This is clearly not drawn to scale. All right. 16 inches, and so the altitude on AB is 6 inches. All right, A, B, C. How about that? All right, then what?
BC needs to be extended.
BC is extended?
Yes.
Okay, so it's extended through C?
Yes. To D.
Okay, such that,
CD equals 4 inches.
all right, so this little extension is 4 inches. I assume they have us drawing this down. What are they looking for?
The area of triangle CAD.
Ooh, the area of this triangle.
Yeah.
Interesting. Okay. Thoughts? Jamie?
Maybe start by trying to figure out the area of ABC.
I mean, I could find the area of ABC easily enough, I suppose. I'm not sure if that would necessarily help me, though. Oh, I know how to do it now. Okay. For a minute, I'm like, I don't know if I remember how. I figured it out. All right.
I did.
You did?
No, I didn't.
You didn't. Okay. Yeah, this one was a doozy. I'll give you that. Okay. You had to think back to Theorem 72 for this one. Just kind of throw that thought out there. At least the way I'm thinking of doing it. Maybe there's another way to do it, but the way I'm thinking of doing it. All right. No idea. All right. Here's my thought. I'll just kind of walk through my thoughts, and we'll see if some of you had the same thoughts. My first thought was it's isosceles, which means when you draw this altitude, it does what to the base class? Bisects. 8 and 8. I also, when I draw this, I form a pair of congruent right triangles. How big would the hypotenuses be? Can you do it in your head? Or on a calculator? 10. 36 and 64 adds to 100, square root of 100 is 10. So know that this little piece, BC, is 10 inches, and this little piece here, AC, is 10 inches. Now, here's my thought. I can find the area. Let me kind of rotate the picture here. Right? So I'm going to rotate it this way. And I'm going to put BCD here, where I've got a piece of 4 and a piece of 10. And then I've got AB here, that's 16. And there's this little guy here, correct? All right. Now, with this, here's my thought. This original triangle and the whole triangle obviously share this angle in both triangles, correct? This angle B is in this triangle, and it's in the whole triangle. Theorem 72 says that if two triangles have an angle of one equal to an angle of the other, their areas are to each other as the products of the sides forming the angle. So this triangle here, its area, ABC, is to the area of the bigger triangle, ABD, as the product of the sides BC and AB, and the sides, the BD and AB, is kind of my thought. You follow? Now we know that BC is 10 and AB is 16. 10 and 16 gives us 160 when you multiply. BD is 14, AB is 16. When you multiply 14 and 16 on a calculator, you get, help me out, 224. 224, thank you. So if I knew ABC, which, Jamie, I do know the area of ABC. 1/2 base times altitude. Class? 48. I know triangle ABC's area is 48. Therefore, let me get rid of the middleman here. I can find the area of the whole big triangle at your seats. What is the area of the whole big triangle? Call it? 67.2. All right, got some confirmation there. 67.2 is the area of the whole big triangle when we cross multiply. But I didn't want the area of the whole big one. I just wanted the area of this one. So the whole thing's 67.2. This piece is 48. How big is that? 19.2 inches squared. Now, is there an easier way to do it? I don't know. That's the way my brain thought of, all right, was to use that method. I have no idea. The answers aren't in my book. There's a whole big other book that has all the answers in it, but I leave that at home. And anyway, so no, I come up with I am the answer. All right. So anyway, there's our answer. Now again, is there another way? Maybe so. Maybe I'll look at the solution key and I'm like, oh, that's how I could have done it. That would have been easier. But that's the way my brain saw. Questions on this? I am the book.
No, Mr. Dasky is the math crypt keeper.
Questions? All right, turn over to page 252 now. And let's begin reviewing for this test coming up on Wednesday. Number 2, on page 252, we're dropping down to that section that says Numerical Applications. And go ahead and read that for us if you would, Audrey. At your seats. Go ahead and do so. Side of an equilateral triangle, 6 inches. Find the area. Chris has it, I believe. Yeah. What you got, Chris?
I have 18.
Ooh, that's not correct. Rework. Remember, I am the answer key, so just kidding. Obviously, area is a half base altitude, right? I know the base is going to be 6 inches because all the sides are 6 inches, correct? What's the altitude, anyone?
6 inches. 3 times square root of 5.
Hmm?
I'm trying.
What did you say?
I don't know.
No, say that again?
3 times square root of 5.
Okay, I thought that's what I heard. No, it's not 3 times the square root of 5.
3 times the square root of 3.
3 times the square root of 3. It's a 30, 60, 90 right triangle, where this piece is 3, as is this piece. X, 2x, x squared 3 class?
15 times the square root of
9 times
Half.
3.
9 times the square root of 3 inches squared. Folks, equilateral triangle, 30, 60, 90. You've got to associate the two together. Question.
We're on number 2.
We're on number 2, right?
Yes.
Else not.
Okay, questions? All right. See if we do better on number 4. Read number 4 for us, if you would. Chris.
On the area of a rectangle with the diagonal is 24 inches and one side is 18.
At your seats. Do number 4. Always good to start with a formula, right? R equals BH. The way I rotated it, my base is 18. They told me the side was 18. I can pick that either to be base or altitude. I'm making it base. So all I need is the altitude. How do we find the altitude here, class? Pythagorean theorem, right? Hypotenuse squared equals leg squared plus leg squared, where one of the legs is that altitude. Of course, we wouldn't want to leave the square root of 252. We'd want to reduce that down, wouldn't we? What square is in 252? 36 times,
7.
and so we'll reduce the altitude down to 6 times the square root of 7. There we go. There's our altitude. What's the area, anyone?
108 times the square root of 7.
Okay, 108 times the square root of 7. That was inches again, right? Yeah. Inches squared. Because we don't want to lose that half a point on the test or a point on a quiz, do we? Questions on number 4. Let's drop down to number 6. Read that one for us, if you would, Kendall.
Two semi-polygons have corresponding sides 15 inches and 6 inches. And the area of the first is 2,700 square inches. Find the area of the second.
All right, seats. And how many got 432 square inches? Now again, you could work with the 15 squared and 6 squared. Your calculator handles all the big numbers anyway, but if you reduce out a 3 to get 5 to 2 and square them both, then you get a little bit smaller numbers, which I like, though I still use a calculator anyway, and get the 432 inches squared. Questions on number 6. All right, number 7, read that one for us if you would, Ethan.
2 similar polygons have areas 400 square inches and 6.5 square inches. The side of the first is 15 inches. Find the corresponding side of the second.
At your seats, number 7. All right, same formula, right? Areas to area, side squared to side squared. Plug in your areas, plug in your side that you know 15 squared is to s prime squared. And could you do 225? You could. But I can take the square root of all of these easily. 20 is to 25 is 15 is to s prime. In fact, I further reduced and said 4 to 5 equals 15 to s prime, and got 18 3/4 inches, or 18.75 inches. How many have that answer here? All right. Do anyone need to see it without the reducing stuff? Just plain old plug it in the calculator. We want to see that. Okay. All right. Let's drop down to jump over to number 10, and go and work that one. Diagonal of the square is 20 inches. Find the area. Just two ways to do it. Diagonal of the square is 20 inches. Two ways in which you could find the area. There's the easy way. And there's the hard way. How many either way you worked, you got 200 square inches for the area. Again, to me, when they give you the diagonal like that, piece of cake. Plug in 1/2 d1, d2, because the square is a rhombus. Or, if it's 20, which is x squared of 2, to find x, I would divide out the square root of 2 to get 20 over the square root of 2. And then, of course, there's all the rationalizing. Square root of 4 is 2, and then canceling to get 10 square root of 2, right? And so we could do side squared. 10 squared root of 2 squared, square root of 10, 100 square root of the square root of 2 to get the radicand of 2. There's your 200 inches squared. Questions? All right, down to number 11. Read that one for us, if you would, Quentin.
The perimeter of a rhombus is 104 inches, and one diagonal is 48 inches. Find the area of the rhombus.
All right, interesting. They give you one diagonal and the perimeter, and they're asking for the area at your seats. I would draw a picture, by the way. Thoughts? Talk to me here.
Doesn't perimeter equal area?
Oh, heavens, no. Almost never. Almost never would perimeter and area be equal. No thoughts at all? Let's just suppose we wanted to use this formula. What would I obviously need to find? Diagonal 2, right? Thoughts on those two diagonals?
45
No.
Equal.
They bisect each other, right? So if the whole thing's 48, thoughts? Yeah, 10, 24 and 24. Other thoughts?
Pythagorean theorem.
They're perpendicular to each other. So if I know I've got a side of 26 and a side of 24, I could use the Pythagorean theorem to find that little piece. Find it, call it when you've got it.
Or 10.
10. And if that piece is 10, how big's the other part? 10. So how big's the whole diagonal 2? 20. Oh, okay, so rhombus is half of 48 times 20. I'm going to cut the 20 in half real quick to get 10. And what's the area? 480 inches squared. Questions, comments, number 11. And creativity in your thought. Right, coming up with a way, thinking, what do I know about a rhombus? Well, I know the diagonals bisect, I know they're perpendicular. Oh, there we go. Pythagorean theorem. Hiding in there. Number 12. Given the area of an equilateral triangle, finding the length of a side. Finding the length of one side. Every time we see an equilateral triangle class, we always end up with what? 3069. Every single time we have an equilateral triangle, we always wind up with a 30, 60, 90, don't we? Let's go ahead and label our 30, 60, 90 real quick. Thoughts? ABC. How about x squared 3 and 2x? Now, that means this is also x. That's x squared of 3, and that's 2x, correct? But I'm talking about the area, so I should probably write the area formula also, shouldn't I? T equals a half BH, right? But I know the area. Is a half, what is the base? 2x. What is the altitude? X times the square root of 3. And where I can take half of 2, they just cancel cleanly, so that 48 class is going to equal
X squared times 3.
Where of course we need to divide away the square root of 3 here to get 48 over square root of 3 equals x squared. Of course we don't want to leave that radical in the denominator, do we? So we'll say x squared equals 48 times the square root of 3 over 3, right? Multiply top and bottom by square root of 3. And then that simplifies down, stay with me, to 16 times the square root of 3. So x squared equals 16 times the square root of 3. What do we get when we take the square root of both sides?
X equals 4 times square root of 3.
X equals 4 times the fourth root of 3. Remember, we multiply the indexes when you take the root of a root. And inches. That's x, but that's not what it asked for. What did it ask for? A side. What's a side? 2x. So what's a side? 8 times the fourth root of 3 inches. Homework for this evening is to do page 252 to 253. 252 to 253. Numbers 1, 3, 5. On number 5, I want the area. It doesn't ask for the area. I'm asking for the area. Number 5, I want the area. Write yourself a little note there. 1, 3, 5, where 5 you're finding the area. 15, 18, 25, and 27. Your test is coming up in lesson 167 over sections 5.1 to 5.13. 5.1 to 5.13. Again, the numbers you're doing for homework, 1, 3, 5, 15, 18, 25, and 27. Just those 7 problems. Have a wonderful rest of your day. You are dismissed.